So you should partner loss of this, and you that public happening. You know, also it's all this to later maybe
I did. Well, spoke to Tony. Class. I should say.
Yeah, you did that was later you stress.
Just a little further outside.
I'll find a way to do all this next time when you're not around. Yeah, efficient way.
Well, I've reviews on that.
I keep requesting the CT people that they should fix a camera in 410.
Well,
So the university should do that, and because I think we are recording sufficient lectures that we can justify the expense associated with.
Yeah, I think
Don't listen.
I think it's a good idea. You know, they should have a camera specific for that room, so it's not only your lectures.
Yeah, that's what I'm saying. Whenever CT does it, that's exactly what they do. But it costs a lot of money for that, and then they have to justify what's the right thing to do. Is that room the most important room in the university? They think in terms of the whole university. They come to the decision that if you already have enough facilities, other departments need more.
But I think it's the most important for the physics department.
Yes, for us, that's a way we say. I mean, that's always a challenge, right? Oh, we want it, but then from their perspective, they have to justify the whole university. It was very unfortunate. I think during 2 years after COVID, I wrote this email, and they were very happy because I have all these recordings, and they were very satisfied. Oh, this is great. We would like to spend money on this. And then after they analyzed, they asked the Christians, so how did you do all these recordings? So why are we putting the camera? So they came up with this argument. So I said, oh, we have this camera, which the department paid for. And that's also, if you have it, then why are we spending on it? So keep doing it. So the whole thing fell apart. Yeah, it sounds lame, but again, from their perspective, they're saying that the other departments don't even have that thing. Yeah, it sounds unreasonable, especially I got all excited. I shared it with the whole department. See, just one email got us this. Everything fell apart. It was a little embarrassing.
It's like we're supposed to be like an R1 institution, and we can't give these basic things to the departments.
Thank you. Again, like, instead of putting it that way, I would say if you have $100, you have to spend it. Would you say that this is the most important thing that the university has to spend money on? And it's not $100, remember. When the university does it, they have to worry about a lot of liability. They think about 10 years, not 2 years. So it's for $10,000 for it. When the university puts this camera, they have to put a very good quality camera which lasts for many years. And it will easily be a $10,000 project. And then you say $10,000, is that the most important thing for the university at this juncture? Then you might say that, oh yeah, maybe it's okay.
No, I think we should put another fountain in Campus Lake. That's a good use of millions of dollars.
That also has its purpose, I would argue. Just for argument, but if I had to vote, I will not vote for it.
Right.
But I think that is a point at least everyone makes.
We're just building that welcome center.
Welcome center. Yes, we need a third welcome.
Yeah, I'm not sure.
Yeah, even I hear that one is someone just, for example, like us, someone from the university or outside from the university, they just give a money to build that building. That's why they build that. Yeah. Otherwise, they want to use that money somewhere else. But that particular person, he want to make that. That's why that building. I hear that. I don't know exactly.
Sometimes these things have a way of working out. At least I remember in the university I went to during my time, there was a similar thing. There was a student center, and they spent millions of dollars just renovating it, making it beautiful. And at the time, exactly like this, why are we spending all this money? We need so much money for the lab. But that really made the students use the student center. And in the next 15 years, now this is the hard part, that is that student center really contributed to that. At least when you look at it, you see students spending time in the student center much more than other student centers I have seen. So yeah, it's like saying a home, if you make it more comfortable, it probably improves the quality of the product that comes out of it. But many
I
will justify
thought-
that no, it's not.
Whatever I hear for everyone who ever talk about that building,
Yeah,
nobody likes that one.
No, I hear it. It's I hear
The
it.
biggest issue with it is just remove what was already restricted parking availability
Yeah.
for students.
Yeah, they remove the parking and then make that building. The building we already have other welcome center. That's why they may use that one somewhere else than there.
No, no. No, I hear you. I'm not arguing either way, but often these are a little trivialistic way of arguing.
Maybe they
It's
think-
what I should be more constructive.
Oh, okay.
So, Pradeep, I received a quiz, but everyone else says
They have exam, that's why.
you want to submit.
It's okay if nobody want to submit, then
Is that okay?
I didn't want to.
Our argument was
Yeah.
a couple of us forgot about it, and so he said, "Let's just everyone forget about it."
Okay,
Yeah.
if that one, then it's okay. I'm sorry, I didn't know about that. I thought everybody submit, that's why I immediately submit.
Because there is this clause in the quiz that if nobody submits, then
That's
it,
excuse.
then there is no quiz.
Okay, that's.
So you can team up
We
like
do
that.
this one at the last day.
I disclosed it only in the last, or I emphasized it on the last lecture. So don't talk about it to the next batch. Okay.
Unfortunately, last day we do. Otherwise, we have.
This is the last class I'll have in suggestions. Like this information does nothing for me now.
Okay, so the last class, this last day of the semester, but we still have a homework due. Officially, I cannot make homeworks due beyond today. So homework is due today. But informally, you can take your own time. Right? There's no deadline. Final exam is December 12th. If there is a final exam at all, it's from 8 to 10. So that raises the question of where is the final exam? It's a take-home exam. I think I have posted one question already, and I am seriously debating making it completely take-home. So keep a watch on it, right? So keep looking at the homework. And the benefit I have is that I thought the Green's function at least a little bit, some of you understand. And I feel if I put in more examples, more detailed examples, probably you will get it at this point. So I'm going to put in 3 Green's function questions very similar to each other. I cannot do that if it's a normal exam because that will be too much to ask in 2 hours. So at the price of assessment, I will give away. And I think we have assessed enough. I have enough points to assess. So what happens is that if you participate well, you probably get 100% in your final exam. So if you did very well in the previous, then everything averages out exactly like earlier I said. So if there is a little bit of more ace, I don't mind. Okay, is that clear? So work hard. Don't. I know there are tools out there which makes it very easy these days. I don't mind you guys using it at all. And specifically, I mean AI tools. I tried it out. I mean, I think it was the second midterm. I was quite surprised. I made a question on my own, and I thought this is really cool. So let me give this to AI. It may not know it, but it got 100 out of 100. Like, it was great. So and I didn't expect it again. Like usually you expect certain problems, especially contour integrals, like Mathematica struggles. It is good. It almost gets it always, but still they struggle sometimes. They make mistakes. But it did not. So what I mean here is that AI is good. You can use it. I will encourage you to use it. I think if you do it in the right way, that's okay. I'm not against using it. But if I see that you're not understanding the concept when it becomes obvious sometimes when you see the homework that no, this is not okay. So then I get discouraged and then I get disappointed. Then I have to make this assessment more up there. So be nice on learning stuff. Time is also limited, so it's okay. Again, it's okay to use AI, but be responsible. That's what I'm trying to say. It's like using Google search. It has its benefit, but don't copy it down. Like don't copy down everything that is coming out. Try to understand and be critical about what you write. So, so with that feature, so currently, so there will be 5 questions. And currently one is out, one uploaded. And expect more if
We expect every day one out.
Huh?
We expect every day one out.
No, I think
It's like an advent calendar, but for example.
no. If everything goes well, I think because I think 2 of the problems I have it with me is just I have to rephrase it as a problem. I have it as notes in a way, or they are in the form of homework problems. So I have to phrase it as an exam problem. So I will just rephrase it. And 2 problems I had to build, so that might be the ones that take time. But I would like to get it done, if not today, by tomorrow or late the end of tomorrow. Okay, so if I cannot get it done, then you have an exam. So, so give me more time, or give me make me relax so that I get finished. So if you don't get it done by Saturday, I'll probably make it an exam, because then it's easier. I just have to make a 5-minute question, so that's much easier instead of making a whole 2-page paper. Okay, so that's the way I think, at least. Okay, okay, so that's final exam. There is also this breakfast, and which it is at 10:30, right? Okay. Yeah. So, and I think this is the time when you can start asking where do you want to go. Yeah, so that's up to you guys. If you have anything, you can decide on it now. I think you have a group, right? So you can discuss among yourself and
We will discuss and then let you know.
yeah. Make it faculty friendly a little. I think every place is faculty friendly. Right?
Yeah, I don't think most places like run you out with a broom in a hand or anything like that if you're faculty.
Yeah. Okay. Anything else I should bring up? The last lecture.
I think just my concern. I want to take a picture of all of us with full of the board.
Full of the?
When we are done with the class,
Uh-huh.
I want to make one picture for all of us.
Okay.
Can we make that?
Yeah.
Okay, thank
You
you.
want to do it now?
When we are done at the last,
Okay.
after completing the class.
Like this, you look like you're all clustered. Otherwise, you're all stretched out. You're these days you're clustered a little, so it comes up myself. Okay, yeah, most welcome. Just anytime. Yeah. There is this anywhere there, right? But yeah, there are no people in here.
Yeah, I think I have the attachment for my phone in there. I just put my phone on a timer and I'll just step back. It's very convenient.
Something like that. Okay. Yeah. Sure. Okay. Today, what I thought I'll do is that most of the time when I'm doing special functions, I'm emphasizing the completeness relation and the orthogonality relation and the nature of the vector space, or you should call it a function space that it forms. Today, I want to primarily do your homework 11, last problem in your homework 11. And that is how most of the time you use the special function. So you will see that even without knowing most of the details, you can use it at a user level pretty reasonably. But before I begin, there was this suggestion that there was a quiz that was due, and you wanted to see how what is the functional form of Bessel functions for large uh, uh, for large T. So this is a quiz you had. Remember Bessel functions. Let's say Jm of T is equal to. I like to put the I here so that it's easier to remember. But if you're thinking of Bessel function, you have to put this to the left, or I should say right. And this is equal to 0 to 2 pi d alpha over 2 pi and exponential of it sine. Let me write it as the vectors first minus im alpha. That's your Fourier eigenvector if you want. And that is it the sine alpha. So in a way of saying it, what is the Bessel function is a Fourier transform of this function. That's one way of looking. This is the more modern way of looking at it. By modern, I mean at last 100 years, when integrals became much more easier to deal with. Most of the time, when Bessel functions started, it was represented as a series. For our purposes, when you think about as a t dependence, this is t, this is g of jm of t. This looks like this. Like it seems like it's oscillatory, and then it goes down very quickly. One of the big challenges, if you're working with, I think, if you ever imagined a circular drum, like if you're into music, you will call it a drum, right? A membrane, and if you hit on it, it vibrates, and there is a sound that comes out of it. That's decided, and then you ask, what are the sounds that you hear? That's decided by these roots. Like, where does this go to zero? That's pretty challenging, at least at some early level. If you want to try to find the roots, for example, if I tell you sine function, what are the roots? That is easy. But for this, finding the roots itself can be quite, at graduate level, it is quite challenging. So if you find a new way of finding it, it is quite nice. But anyway, so this is your Bessel function, and the idea is that if you go very large, so take t very large, much greater than 1, then what is jm of t approximately? And the claim is that this is either a sine function or cosine function. And there are some details in there. It pretty much looks like sine and cosine. Of course, its amplitude goes down. That's where this sign comes in, that it is, as far as you don't worry about the amplitude, the oscillator part is completely sine and cosine. Let me see. Is there something you would like to add to this diagram? Does every Bessel function look like this? There's a homework problem where I ask you to plot. Do I ask you to plot? Probably not.
Yes.
Yeah,
Have you plotted it? Has anyone plotted it yet?
I have not. I usually say the plotting last.
Right.
Huh?
J0. J0, yeah, good. This is J0. This is J0. What will be the difference between J0 and J1? That's good. So J0 starts from 1. Everything else, so this is J0 of t. That starts from 1, like that's like a cosine function. It starts like 1. And rest everything starts from 0. And I might be wrong. I don't know exactly where these roots are. Right? So they will also go down And the roots, the main idea is that for the mth Bessel function, what are its roots? They have physical implications usually. For example, for the drum, what will be the harmonics is decided by those roots. And usually the roots is what, if you're looking for energy in a problem, then the roots come into picture. But anyway, what is the differential equation satisfied by Bessel function? It is minus del perf square plus k perf square times jm of t is jm of not t. You would say k per rho is equal to 0. I can expand this out. This is 1 over rho, d by d rho, d by d rho, and help me. So this is, I think, 1 over rho square. Yeah. So basically, your Fourier transform to the z direction, if you will. K per rho is equal to 0. If I'm working with m, this practically gives you the m square in it. So somewhere there is an e raised to I m phi. All the angular directions has been Fourier transformed into e raised to I m phi. So when I take the two derivatives there, that gives you an m square and probably changes sign. Let me check on this. Because when I take the differentiation, I'll get a I times m. So there will be, so to 0. And can make sure if I wrote that equation correct. Apparently not. Oh. Yeah, okay. This thing I read it as plus minus. This is correct, and this is minus account. Is that so?
The one is plus in the equation.
That could be wrong, right? No, this is. Yeah, this is correct. Yeah, so because I'm looking for also, yeah, so this is this differential equation satisfied by Bessel function minus a square. So there is a put in all the minus signs out. Minus, and this becomes plus. Yeah, it's okay. Okay. Better. So this is the differential equation for the Bessel functions. There is a second derivative with phi that comes in, acts on the exponential, it gives you m. Again, always think of it as this is coming from k per is coming from exponential of ikz, but here you're thinking of it as dying function, so it is exponential of minus k per z, and if you want, this is coming up. So this is the derivative that is given. So it is the derivative acting on this. And m, I times m is coming from d by d phi, and rho stays the same. Does that help roughly? But anyway, for our purposes, we have this differential equation. Let's also put k per rho as t, just to make it a dimensionless quantity. Then the whole thing can be written as minus 1 over t by t. That's the one derivative at this point, plus m squared over t squared plus minus this minus 1 times a m t is equal to 0. For seeing the functional form here, so the following trick is what is needed. So let me see. So let's try to, just as an exercise, let's try to find out what is d by dt. Again, there is only one parameter here, so there's no need for writing partial derivative. There's nothing, no catch in that. It's just the moment you write a partial, it seems to convey that there's another parameter. This is acting on a function. Let's say there is f here. It could be a function of t. Then let's see what this gives you, 1 over root t. I can hit this on the root t, which gives me 1 over root 2 by a root t comes in the denominator, acting on f, plus acting, if it directly acts on f, it is d by dt of f. And that seems to suggest that this is equal to 1.
Should there also be a 1 over root e in the
here?
second term?
This cancels out, right?
Oh,
Doesn't it?
good point. Good point. I
Think
did
so.
not see that. I
Yeah.
apologize.
Think so. Plus 1 over 2t times f. Right? So that's how we would see. Is that correct? Think so. So again, look at this expression in here, 1 over t, e by dt times t, e by dt acting on f. Again, you can do the same thing. If it acts on this, that gives you 1 over t times 1 over t times there is already a derivative acting on it. And if it acts on the second side, it is second derivative of f. And the idea is, can we use this somehow? Let me refer. Yeah. Okay. So that's what we have. And again, let me write this as 1 second derivative by dt squared plus 1 by t by t acting on f. Do this twice because I want a second derivative, right? This is the first derivative. I would like to get this somehow. So apply this 2 times. So you have 1 over t by dt times, which is the same as this acting. The thing, this acting twice would mean expanded form of this. These are 2 derivatives that comes out straightforward. So that's d by dt squared plus, let me say this one. That's 1 over 2t times d by dt. Here I have to be careful because it can hit on the 1 over 2t or f. And the last one is plus 1 by 4 t squared times f. I just have to worry about this. So this is equal to second derivative of t squared and if I hit it on this, I get a minus 1 over p square. Right, minus 1 over p square. And d by dt of f. So, and if I do the opposite, I try to do the other one, I get 1 over 2t. No, this is wrong, right? So the dimensional is wrong. So there should be only 2 times. This is not there. When I hit it, so you can hit on this or this. When you hit on the first, there is nothing else. Okay, this is correct, I think. So these two terms add up. That's the important point. Plus 1 over t plus rest of them add up as plus how should I write this? Half is greater than 4, so this is minus. Good. So that's a identity if you want. Use this to rewrite what is this here, right? So that means that this is equal to let's say put this in here, equal to minus, so it is minus second derivative of dt square over minus 1 over t d by dt, right? That's all. This structure in here plus m squared over t squared minus 1 of j m t is equal to 0. So that's your differential equation. Substitute this in there, and I learned that this is equal. Okay. Oh, I so plus m squared. Well, that should be a true identity. Right. This so replace this using this quantity. So I have minus 1 over root t d by t t plus m t is equal to 0. And so yeah. This is absolutely right, right? Now, so here is so first you write it in this form, and now the argument is that if the order, there are two parameters in a Bessel function, one is m and the other is t, right? If this was very small, that means to say the order of Bessel function is significantly smaller than the t. Or the argument. So m squared minus 1 over 4 is very much less than p squared. It is practically saying that the order of the Bessel function is significantly small compared to t, or you can say this is log, right? T tends to infinity in a sense. So this can be neglected in that case. And what we learn is dt by t squared minus 1 minus. Yeah. At this stage, I can say this is JMT is equal to minus of JMT. I think so. And let's see. So square of this. This is 1 over root t, e by dt, root t, 1 over root t, e by dt, and t. Is equal to minus the big. So the root t here cancels out. Notice this has to act on everything here like this. If you want, there's another bracket in here. Like this has to act on both, and this derivative has to act on everything. But whatever it is, this cancels out. And let me use this root t to write on the other side. And what I learn is that second derivative of t squared acting on t t is equal to minus b. It's okay, very scary. Yeah. Is this a familiar equation? So that's harmonic oscillator equation. That's that's what sine and cosine satisfies. This immediately implies that root t times jmt is like up to a coefficient. This is sine or cosine. Like it could be a times sine of t plus b times cosine of t. So we don't know that exactly, but more importantly, it is some constant a times sine of t over t. So this 1 over t is what is really killing the Bessel function in the large. So there is a 1 over t, there is a, so it is dying off, right? That's the 1 over t going up, and that is plus, which whether it is sine or cosine, you need to do more details for that. Whether it is a or b, you have to do more details. Just for completeness, I think I can tell you that what is the exact form. I happen to have it in my notes. This is more accurately. We do this more carefully. This is still the the constant in the front, you cannot help it out, but this is 2 over pi t. So you get a pi over 2 also that can be pulled out. And more importantly, there is a phase first half pi by 2. So it is always a cosine piece that comes out, but there is this, you can always make this a sine for the right m order. Okay. So that's your that's how it is related to sine and cosine, and that's a very good way of at a practical level when you're really working on problems. You have a model and you would like to guess on the solution. You want to have that is all you need. That a Bessel function is mostly a sine function with a dying piece to it. That's the visual interpretation you want, and then you know that at some point what is the feature that you have. And these are the ways I'm going to use similar arguments here for doing the homework problem in your homework 11. So this will also help you with your. Any questions before I proceed? That's your quiz. So now you can all submit if you want. But no, let's not submit. I don't want to grade anymore. Like every submission requires me to grade. So these are Bessel functions, and there are similar things that we talked about here. Since we just discussed this, it's good to have there are sine and cosines, right? Sine kx, and for every second order differential equation, you need two independent functions, sine and cosine. So that is that again, for completeness, you need both such functions. Usually the feature is that one of them dies off at large x, one of them dies off at small x. So that's usually how you differentiate it, especially if it's a position parameter. When we have sine kx and cosine kx, by the way, how do we check whether two functions are independent in a differential equation? Like we did a lot of differential equation. I didn't stress on it, but the understanding is that you study the basics of differential equations somewhere else, usually a math course. How do you know that sine and cosine is indeed independent? How would you check it?
What do you mean by independent?
By independent, like for example, let's say you usually say a differential equation that this is satisfying the differential equation f is equal to minus k squared f, correct? And you immediately say that, oh, I have f is equal to a cosine kx plus b sine kx. Who says that there should be only two? Maybe there are three, there are five, or y sine and cosine. Like for example, I can also say this is one possibility. The sine kx plus, let's say, d e raised to I kx. Is that okay? Like, out of this, which are the correct ones? Let's say a d, let's say e raised to I kx plus f e raised to minus I kx. Right? Is any of this right? Like when you propose a solution, you can see that cosine kx satisfies this. Sine kx also satisfies this. In fact, this will satisfy it. For any a and b, you will satisfy this. Will this satisfy that equation? Will this satisfy that equation?
Yeah, the minus on there and the minus. So it seems like both the bottom two satisfy.
Yeah. Did anyone comment? All of them are true solutions. So is there a guideline? Can you use any one of them? Is it okay?
I don't see why you can't use
Yes, exactly. You can use anyone, but then I say, why exponential? Is this okay? So let's say e times cosine kx plus d times x cubed, for example. That's also a function, right? You might say that, okay, that doesn't satisfy it, but yeah, that doesn't satisfy the equation itself, right? So that's not a good example. Yeah, I'm not able to build one. Okay. But okay, so but the main point I want to make is that what forces you to decide which combination to use, or if there are three such solutions, how do you know that this is not a new one? Or maybe I should say, yeah, how about this? Why not use this to be the solution? Maybe the argument should be this, and this happens in Bessel functions. sine of minus kx is also a solution, right? Or minus kx, or yeah, not I. Like that's also a solution. So why can't I treat that as an independent solution? So the argument here would be that, let's say k prime.
Does it have to do with there are certain like boundary conditions that can be satisfied with that solution?
Or it has to be independent. It's like saying if you have two unit vectors, I hat and j hat, if you have a vector space, I can expand a vector in terms of this, or I can even expand in terms of different E1 and E2. Any two eigenvectors are sufficient to expand a vector as far as they're independent. If they're along the same line, then they're not independent. One can be written in terms of the other. Right? Is that should be very familiar in two-dimensional vector space. If both the vectors are along the same line, then they are not independent. That's what you would say. So similarly, there is a constraint here also. You cannot choose two functions which are dependent on each other. That means to say that there should be a check. How will you check that two functions are independent? Like in this case, you would say orthogonality conditions, right? That's a very simple, intuitive way of saying that. Most of the time, whenever there is a differential equation, what do you use? The first thing you learn in a partial differential equation course, or probably differential equation course, Wronskian, is that familiar? Right? That's the importance of a Wronskian. So Wronskian of two functions, f1, f2. If this is what is the Wronskian of a function? Whatever the differential equation satisfies. So it is f1, the determinant of f1. First write a row out of it, and then take the derivative. In this case, it is a derivative. It depends on the what is the Wronskian is decided by the differential equation in principle. So this is if this is equal to 0, that means they're dependent. If they are not equal to 0, then they're independent. So you want it to be not 0. If it is 0, that's not good, right? Or that's not a good solution. Okay, so that's why you need sine and cosine. Okay, I have only half an hour. Last lecture, I cannot go beyond. Okay, so let's do this quickly. Any questions on that before? Okay, so you can test that sine and cosine are independent. And what was I saying? Yes, but the moment you have trigonometric functions, there is a way of going into a new space. Often, especially when we first time see this, they're called hyperbolic functions, right? I think one of you guys is doing a project on hyperbolic angular momentum. That's, I think, a very similar idea. That if you go from k to ik, this sounds very innocent, but it is an entirely new space, and its features at infinity change significantly. What happens if you do this substitution? What is a new function that comes up? That could be familiar.
The hyperbolic sine.
So that's a sine hyperbolic. All right. So this is sine hyperbolic kx, and if you do the same thing here, it's cosine hyperbolic kx. Right. And there should be an I here, so this is approximately, let's say, right, up to a constant in front of it. What happens here, and you can build a whole trigonometry using this, right? You have sine square x plus cosine square x is equal to 1. Here you have cosine square x minus sine square x is equal to 1. And there's a whole trigonometry, as far as user level, there's a whole trigonometry associated with it. Here, these are oscillatory functions. How does sine and cosine look like as a function of x?
Parabolic.
One, which is parabolic, or so cosine.
Yeah.
So cosine is, so this is cosine hyperbolic x. It goes from 1, and sine hyperbolic x is like this. And it is exponential. Remember, these are e raised to kx. plus or minus e raised to minus kx over 2 or 2i, right? Like that's here. So for large x, one of them dominates and it is always exponential. So for our purposes, for large x, this is either plus or minus kx. Sine hyperbolic and cosine hyperbolic are plus or minus kx. You want to do the same thing here. Okay, for Bessel functions, there is another function in here. Most of the times we are having radial coordinates, so we don't need that other function. So Bessel function, now this is called modified Bessel function. Or since I have short of time, let's go with the differential equation. Yeah, this is what was the differential equation for Bessel function? Minus L perp square minus, right? Minus k square plus. What was the differential equation we wrote this now?
Yeah, minus del perp squared minus.
Minus?
Yeah, and then there's a.
Oh yeah, because it's exponential minus k. Yeah, okay. So, and then we have JMP, right? JMP rho is equal to 0. Is that correct?
Is it not k perp? I mean, I guess it doesn't really matter, but.
Yeah, I'm going to not worry about that because if I bring in the geometry, then I have to explain why that is there. As far as we are concerned, that's just a parameter. At least the way I have been emphasizing it, I call it a perp, and then I replace it with a z, right? So, but it's just a parameter, for example. Here, what we did is this was the important piece to go from a normal trigonometric function to a hyperbolic trigonometric function. We do the same idea here. K going to I times k. So this is minus del perp square plus k perp square. And now these functions are called, there are two types of functions. There is km of k rho is equal to 0. And there is a second set of functions. They are called Im k rho. Exactly like sine and cosine. So that's equal to 0. It's good to now you see this in your homework. There is a homework problem also. How does this integral representations change under the substitution? You will see that in your homework. For my purposes, the only thing I need is that if I were to plot, remember we plotted Bessel functions, which are oscillatory, sine or cosine. These becomes hyperbolic, they start growing or they have to die, right? So this is as a function of t. I's grow, so this is IMT. There is a small feature that if it was a 0, it starts from 1. So this is IM and this is I0. The important feature is that they grow exponentially. And at 0, there is a small feature that it starts from 1. That's a detail in there for our purposes. They all grow exponentially. Okay. The other function, k of m, they die. Right? So this is km, all k's. They die. Okay. So if I say that a problem cannot have an infinity for t equal to 0, that means you cannot have k's for that. Like exponential functions, you cannot have if it is on the right side or the left side. Same idea in here. Any questions on this? Okay. So now let us say you're doing a differential equation and you have these features coming in. I will just make a point without trying to motivate that much, that if you were to solve for a cylinder, a conducting cylinder, you are doing electrodynamics parallelly here, or at least some of you are doing electrodynamics. If you were to do electrostatics or magnetostatics for a cylinder, these are the functions that will come in. So the differential equation you will encounter there is minus 1 over rho d by d rho, rho d by d rho, and who has the homework with them? Oh, yeah, right. Me? Yeah. So this is a differential equation that shows up in your homework. Or this is
G1 in the homework.
rho prime is equal to. That's if you were trying to find out what are the solutions possible for a conducting cylinder, that's a differential equation you will encounter. This is a charge you're talking about, so it's not an empty cylinder. You're placing a charge inside the cylinder, inside or outside the cylinder. You can keep the charge anywhere you want. And you ask what is the potential everywhere. That is the challenge you will have. And if you want to solve for this problem, you would like to say that this is representing an electric potential. So you would say Gm of 0 for any rho prime, wherever the charge is, at 0, the potential cannot be infinity, right? Not equal to infinity. It has to be finite. That's what you're saying. Similarly, Jm 0, rho going to infinity of rho prime cannot be is 0, let's say. At infinity, you cannot even have a finite feature. You would like it to go to 0. For rho not equal to rho prime, that means to say you never say what is the electric potential on the charge, right? Rho prime is the position of the charge, so you want to stay away from the charge. In that case, you have minus 1 over rho d by d rho, rho. What's the right hand in that case? Rho is not equal to rho prime.
Zero.
Yeah. 0, right? Very good. And the moment it is 0, you know the solution. Right? That's your Bessel functions. So you would say there are 2 Bessel functions and in 2 regions. Right? So that's your Green's function idea, that there is A times I, one is dying. So let's say I m. This is the inside part, I m, and this time you say instead of writing sine and cosine, you write Bessel functions plus b times km k rho. And this is if rho was less than rho prime. That means for regions inside the cylinder. The other solution possible is c times I m k rho plus b times km k rho. And that's for rho prime less than rho. I would like this solution to be 0 for large radius. That means very far away from the cylinder. Far is in here. That means it has to go to 0. That means I cannot have i's in it. If I have an I, it will grow to infinity. So this cannot be possible. So this means that this is equal to 0. Right? This is coming from the first condition or second condition. Yes, Richard.
Are the IMs and the KMs here representative like the hyperbolic?
Yes, yes.
Okay.
Whenever I write J, they're oscillatory. K and I, they're exponentially growing, or these are the hyperbolic. Yes, that's right. A way of saying this would be hyperbolic Bessel functions are what are modified Bessel functions. That's a standard terminology for 200 years, so no one wants to change it. But in a modern way, one could say it is hyperbolic. Just like no one says hyperbolic angular momentum. Like that's not a conventional usage. You would say it is an element of SO21. There is a technical word for that. But hyperbolic is fancy, like
Okay. I
it's
just wanna
a
make
style
sure-
that's all.
Yeah, I just wanna make sure that they follow maybe the same rules within the B11. Or,
Yes,
yeah,
it will be. The only thing I've changed is the sign of this when I go from Bessel to this. Just that putting that I value changes a lot. It changes so much that an oscillatory becomes exponentially growing or decaying. If you're doing numerical calculation, like if you're in experiments or anywhere these days, numerics is now very common. And if you've done any serious form of computation, you will realize that oscillatory functions are very hard to deal with. Like if you want to look at the details, they keep oscillating. It's a zero or something else. It's very hard to capture something out of it. So one of the trick you would use is do a formal hyperbolic conversion. They become decaying or growing, and the oscillatory feature is gone. Get the answer in that space and come back and do the hyperbolic nature to that, and you will get the same answer. In fact, Bessel functions, you typically do this and you can get extremely high accuracy, which is very you don't even expect that this will happen even in the first order of this approximation. So there are standard approximations that deals with it. I'm not using the words, but they're very powerful techniques that people have discovered. But okay, coming in here, we have c equal to 0 because I grows, and you don't want high values at large t, in this case rho. And the same thing in here for small t's, you don't want any infinity here. So this is also 0. Right. So you immediately have two constants gone. So this is immediately equal to, you have now know that here is your I m k rho and d of km. Okay. You still have to find your a and d. Fine. With me until now. So how will you go and solve for a and d now? Anyone?
Continuity.
Exactly. That's the idea of Green's constant. The first two conditions are physical conditions. Like they came from physics. The rest of the two, the equation itself has that information in it. And these are called continuity conditions. Keeping time in picture. I will let you guys do this in the part of the homework, right? That's part of the homework. Derive the continuity conditions from here. What you do is basically you integrate. You have done that in the other differential equations, same idea in here. And there are two continuity conditions. First one is because you want the delta function on the right side. So Gm, evaluate it at rho equal to rho prime plus a small infinitely tiny distance away, and this is minus. This has to be equal to 0. That means basically the Green function has to be continuous at rho, right? Somewhere you have rho here. This is your 0, and somewhere this is rho prime. So if you approach rho prime from the left or to the right, that's what you're talking about, and that has to be continuous. And the second is that its derivative has to be discontinuous, and its discontinuity is in such a way that put your rho prime minus epsilon, and this is equal to, oh, yeah, I can see that. So you basically integrate with rho times because there is a radial scale there. The rho cancels out, and that also cancels out. So I guess I just have -1. So, oh no, there is a 1 over, there is a rho itself. Okay, so that's your continuity condition. So basically, I'm taking this piece in here, multiplying by a rho and integrating it. So rho cancels out. This is a total derivative that goes away. And whatever remains has to be having a discontinuity. And on the right side, this gives you 1 because I multiplied out a row. Integration of a delta function is 1, and the -1 stays, so that's on the right side now. And rest everything comes in. So you should be a very efficient in doing this. If there is an exam and if there is one problem, I still think that I should ask one question. These are the problems I can ask. Like I can give you a differential equation and say what is the continuity condition for this, right? That can be done in 10 minutes, or for a student 10 minutes. But if you're very fluent in it, probably half a minute, right? So, brilliant. So that's your two conditions. Put this in there, and I'm going to write the top first. So greater than sign is in here. So it is d times km k rho prime. I have to evaluate this at rho prime minus of a times im of k rho prime is equal to 0. That's the first condition. The second condition is I have to take the derivative of this. Derivative of a Bessel function, that's a complicated feature. So we just write that as so derivative of IMT will have the notation that IM prime t. If the argument has a k in it, so d by d rho of IM k rho would be equal to prime means the complete argument. So I have to provide a k there. Like that's you're taking the derivative with respect to the argument. That's the idea. And then do the same thing in here. So I have k times, so this is d times km prime of k rho prime minus of a I m prime k rho prime is equal to that. Should have been a k that should have come out when I took the derivative of these quantities. I put that as k times rho and take it on the right side. This is -1 over k rho prime. Is that clear? I jumped a few steps when going from here to here. Right? There should be a k multiplying this. There's also a rho multiplying this. So, but I'm replacing rho with rho prime. K times rho prime here and here. I write it on the denominator on the right side. That's two equations. I have to solve for B and A. So let's solve for D, right? So the denominator will be equal to the coefficient, this multiplied by this. I'll write that as minus IM prime K rho prime times KM K rho prime. And I'm writing it as on the right side specifically for a reason. And the other term is this is determinant, right? This times this times this, that is equal to IM K rho prime times KM prime K rho prime. Okay. That's how you solve for your D. The numerator will be, I have to replace this coefficient with 1 over k. Minus and a minus cancel out, and I still have a minus sign remaining. So that's 1 over k rho prime times IM k rho prime. The thing is that clear how I got that? The denominator seems to be like an expression for Bessel functions, but this has a nice feature that this is exactly the Wronskian of the two functions. You don't have to know that, but if you do your homework, that's one part of your homework that you will show that this is the Wronskian. Wronskian for I and k, for your IM and km is equal to, remember, IM, km, evaluated at any argument. This is IM prime. You take the derivative, right? As a determinant, that's equal to IM times km prime minus of IM prime times km. And the value that it satisfies is described by the actual differential equation. This you will see in your homework, that this is exactly equal to minus 1 over t, the argument of this. This is t, that's your t, the argument of that function exactly. So this denominator as a whole is equal to the minus 1 over k prime comes in, and this is exactly equal to I m k rho prime. Right? So the whole denominator exponentially growing functions. So notice if d is in the region where rho is larger, right? So when d is in a region, yeah, but this is rho prime, right? Rho prime is smaller in this case, so Im is well defined when it is inside the cylinder. So here we are talking about region. So rho will never reach infinity, or rho prime will never reach infinity because it's bounded by rho. So that's always a check. The exponential features you can see. That's your D. Do the same thing for A. You just have to put this in here. So you get K instead of, so it is 1 over K rho prime, and you still have the minus sign, and this will be Km K rho prime, and the denominator is the same. But that's the Wronskian that goes away, so this gives you Km K rho prime. So now you know your D and A, so you know your solution. So this is Gm is equal to A is Km K rho prime times Im K rho. This is when rho is less than rho prime. And if it's the other way, rho prime less than rho, will be the opposite. So it is Im K rho prime times Km K rho. Notice whichever function has the larger one. So let's say rho prime is larger, right? Rho prime is larger one will have a decaying solution. K will always come with the larger one because there it is well defined. Otherwise, it goes to infinity. Here, the larger one is rho. So the larger one is rho. So it has the K because it's well defined. And the opposite in this case, because K cannot be there because it is infinity. If you use the idea of minimum and maximum, if you use the idea that rho less is equal to minimum of rho and rho prime, this can be captured in a single term as saying Im K rho less times Km K rho greater. And that's your Green's function. So it can be captured very easily. Immediately, since we did how these are, like if there was a quiz today, but I don't want to make it because then you will have a submission. If there was a quiz today, you would say for large rho and rho prime, show that these are exponentials. This should, like since the other one gives you sine and cosines, this should lead to exponentials, and that's a limiting form you can easily take. I'll stop here. I still have almost exact time. Yeah, that's a good timing. Thank you, and thanks for listening.